Okay, so let's talk about tipping points. Our plan today is to think about math and sustainability a little bit, what that means, and then go through these subjects: alternative stable states, then resilience, gradually changing environment, and finally thinking about decision support. So I borrowed this slide from Peter March, who some of you will know from his days at NSF. These are what he thought of as the components of sustainability. So of course they range from energy through ecosystem services, education, policy, economics. This was Peter's view. Math at NSF. Mathematical sciences can tie these subjects together, right? These subjects need a common language if they're going to interact. One of those common languages is English or whatever language your country speaks. But another common language that allows you to get quantitative is the mathematical sciences. So it's an extremely interdisciplinary subject, and it needs interdisciplinary courage. And our students need that courage to be translating between these disciplines. And we need that courage to teach them to do that, because it's much more interdisciplinary than we're used to being. And researchers need this courage. And I think to be wrong in public, mathematicians are used to doing their research in their office. As my father used to say, it takes 17 bad ideas to get a good one. And we're used to having those bad ideas in private. But when you're going to be part of an interdisciplinary team, you have got to be prepared to have those bad ideas in public. And it takes courage. But once you learn to do it, it is so liberating. And it's the most efficient way to learn, is to ask your questions. And then if you're thinking about sustainability questions, you know, this is where we're going when we think about math and sustainability. It doesn't really matter what we believe in terms of climate. The sustainability questions are all important questions for the planet. And a very important part of this slide is the title. When we're educating, it's way too easy to talk about the problems. And it's not good for our students to hear only this doom and gloom. It's incredibly important for us to learn about what are the potential solutions and how can we and our students help contribute to those solutions. And to teach our students that they do not have to be engineers, they do not have to be scientists. Whatever their talent and whatever their passion, they can focus them on objectives like these, or whatever they care about, if they want. I think it's a very important message for us to pass along. So that's one of the most important slides today. Here's another one. This is your homework. Google MPE 2013. So that's the Math of Planet Earth 2013 that we were hearing about. It's an international initiative, and if you do Google it, you'll find that on the homepage right now is the focus on Math Awareness Month. Math Awareness Month is chaired this year by Victor Donnet. You can pick up your poster. And I would like to draw your attention to the energy challenge. So this is designed for schools and colleges. So tell your friends, tell your children, tell your children's teachers, tell your grandchildren's teachers, tell everybody you know in a school or a college that this energy challenge is there. And the idea is that students do some math to design and model and implement an energy-saving action. So they do it, they implement it, they measure the energy savings and refine their model, so they're matching this action with modeling. And then they post this. They post what they've done on the Math Awareness Month site. And so we get from our little local action to a collective national action. And I think this is a powerful thing to teach our students as well. Can you read that? It's a whole crowd of people saying, what can one person do? They all want to achieve the same thing, and they're all trying to achieve it in isolation. And so what we're trying to do with Math Awareness Month this year is go from the local to the global collective. Thank you. And here are some of the partners that have been brought together to do that by Victor. It's a wonderful collection of people. And there's lots more on the Math of Planet Earth website. There's a daily blog. There's a lot under the education section. There's research programs. Just go explore it. You'll also find, I'm going to talk a little bit about climate models, and you'll find much more about climate models on the Math Climate Research Network page. So this is another national network that a group of us have pulled together to bring mathematicians and climate scientists working together. And we ran a short course at the 2013 Joint Math Meetings, an MAA short course. Thank you for that. And everything's on the website. Okay, so that was just, there are plenty of places to find more about math and sustainability. So let's do some math and look at alternative stable states. And we'll have this research theme going on throughout the talk. So I'm going to talk at this level. I'm going to talk about simple dynamical models so that everybody in the room can follow along. Depending on your level of mathematical maturity, you be thinking over here. We have complex computational models that we use for prediction. We have these simple, insightful models that show us the mechanisms and help us understand how the mechanisms behind a behavior work. And it's a huge open question in climate and ecology and medicine and economics and pretty much any application you choose. We've got models at the two extremes and we're not very good at connecting them. So I'll be talking here, but I invite you to think wherever your mathematical maturity can. And I'm going to be talking about insights here, and the question is when, under what conditions do those insights persist through to more complex systems? So here's a complex system. Here's components of the Earth's energy balance. So there's solar radiation, solar energy coming into the planet. And some of it is reflected off the surface, that's the albedo. Some of it's reflected off clouds. Some of it's actually absorbed by the planet. So the planet warms up and emits energy. So here's the energy being emitted. Some of it gets absorbed by the greenhouse gases, and then that heats up the atmosphere and back radiates to the planet, so the planet gets even warmer. Some of it escapes through the atmosphere. If you want to learn more than I'm going to tell you today, and I'm sure you're going to want to learn more than I'm going to tell you, here are some of the books I enjoy reading on the subject. And this one, I didn't have a picture for this one, but look. Hans Engler is here, there, in green. And here's the first time I've ever seen this book, brand new copy of it. Thank you. So what a beautiful cover, eh? So this is borrowed from Hans, where instead of looking at that very complex picture, we're going to look at the simple dynamical version. So we have energy coming into the planet, and it's going to balance energy going out. If it didn't balance we'll talk about what happens. Let's just carry on. So the energy coming in depends on many things, but in particular it depends on the reflectivity of the planet, the albedo. So where there is ice and snow, it's white and lots of solar energy gets reflected back, so the albedo is high. Where it's deep blue ocean, a lot of energy gets absorbed, and it's low albedo. So at the extremes, if our planet had a very low temperature, way lower than now, if we were extremely cold on average, then we would have an ice-covered Earth, and so the energy, most of the energy would be reflected off, so the energy in would be very low. Right? So that's one extreme. Another extreme, if we were way hotter than now, then we'd have an ice-free Earth, so most of the energy would be absorbed, and the energy in would be very high. So those are our extremes, and we can connect those extremes. Here's the way lower temperature than we have now, and here's way higher temperature, and somewhere in between, let's assume that we get from low energy in to high energy in. Okay. Now let's look at the energy out. We'll use the approximation that the planet is a black body, and so black body radiation is modeled by sigma T to the 4, where T is the temperature of the planet. That's classic physics. But we're going to adjust it slightly because we do have an atmosphere, and that atmosphere captures some of the energy that's radiating out. So we'll put an epsilon in front, because not all the energy escapes. So the greenhouse gas process is captured by that epsilon. So there's our simple graph, epsilon sigma T to the 4, of energy out. So now let's graph these together. Let's assume, for the moment, that the graphs intersect like that. And we can write this differential equation. dt by dt, what a wonderful piece of notation. d temperature by d time, the rate of change of temperature, right? So temperature is changing, it's either increasing or decreasing or not changing at all. And that's going to depend on the energy in versus the energy out. If there's more energy coming in than leaving, this will be positive. And so the change in temperature is positive, which means temperature is increasing. If there's more energy leaving than arriving, then the Earth is radiating more heat than it's receiving. And dt by dt, the change in temperature, will be negative. And so temperature is decreasing. That's how to read that equation. That's calculus in a nutshell. So let's do it geometrically. What happens at this point when t equals a? Stable, right, because energy in equals energy out at this point. So this is 0, so there is no change in temperature. So we're at a temperature equilibrium. There we go. You were right. Well done. Same thing happens at these 2 points. And how about in here, in between B and C? In between B and C, temperature, the change in temperature is positive. Why is that? The energy in, the orange curve, is above the energy out. So energy in is greater than energy out. That means that the change in temperature is positive, which means that temperature is increasing. This is our temperature axis, so there's an increasing arrow. If we happen to have a temperature in there, our temperature will increase, according to this model. Out here, it's the other way around. Energy out is greater than energy in, and so if we happen to have a temperature out there, it will decrease. And we can fill in the arrows. What's it going to do over here? Decrease and increase. Right. So all our information now is on that line. So we can extract that line. That's called a phase line. Can you tell the difference between red and blue? Red points are attracting equilibria, and blue points are repelling equilibria, unstable equilibria. And I'm going to take this line and just rotate it. So it's vertical. It's the same line, it's the same information, it's captured a lot of the predictive power of that graph. So we know anywhere we start, we know where we'll be driven to. If we start at this temperature, just below B, we'll be driven down here to this very cold temperature. What's the planet like down here? It's worse than an ice age. It's a snowball Earth. It's totally snow-covered. Up here, it could have ice caps or be ice-free. So our recent paleoclimate history is all up here. Oh, there. Okay, so that's one example of a system with alternative stable states. So the idea is that there are feedback mechanisms within the system which will drive us to one or other of these states. So let's look at some other examples. Oh no, before we look at other examples, let's ask this question. If our temperature happened to get below B, we just said that we would be driven by the feedback mechanisms, the ice albedo feedback, down to snowball Earth. And there is evidence in the geological evidence that 600 million years ago or so, the Earth was a snowball. So, question to you, how did we ever get out of that stable state? It's a stable state. Why aren't we still there now? Say that again?
External change, increase in solar radiation.
Possibly. It would take a lot. It would have to take getting all the way back up there. Yeah, how far would we have to get back? Could be a formation of an atmosphere. Right. Volcanic activity. Yeah, yeah. We'll come back to it. We'll come back to it and see. But let's look at another example. This is one of my favorite books by Scheffer, Critical Transitions in Nature and Society. So he looks at a lot of examples. We'll look at his lake example. So shallow lakes come in a variety of forms, but these are two states that they're often found in. A clear lake where there is lots of vegetation, and that vegetation supports biodiversity. So there's plankton, vegetation supports the plankton, that supports the fish, they support the birds, and the vegetation anchors the sediment. But another state the same lake could be in is this turbid state where algae are dominating, So the lake is dark, so the vegetation dies. So without the vegetation, you don't support the biodiversity. And now without the vegetation, it's easier to churn up the bottom. The fish that live at the bottom now dominate, and so they're churning up the bottom. And it's just, you see the feedback that keeps this in a turbid state, and the feedback that keeps that in a clear state. And here's some evidence from Scheffer's book. The axis here is vegetation cover. The axis here is the number of lakes. So the point being made here is that lakes come essentially in two forms. There are two stable states they can be in. This one has hardly any vegetation, it's turbid. This one has a lot of vegetation, it's clear. And the axis here is time. The axis there is the amount of turbidity. The axis here is, these curves are about vegetation and animals. So the point is that as the turbidity decreases, the biodiversity increases. So there are two different stable states in an ecological example. Here's another example, bursting in excitable cells. So the cells I've chosen to draw pictures of here are from the pituitary. The pituitary is right behind the nose, and it's very involved in our endocrine systems. And these somatotrophs release growth hormone, which is how we grow. And the release is governed by these bursts of excitability in the cell, these bursts of membrane potential. So this is voltage. So there are two states the cell can be in: quiescent, when it's just resting here, or bursting, lots and lots of action potentials. This is just greater detail. And the cell flips back and forth between these two states. But anyway, it's got these alternative stable states. Or if you look at a recurrent neural network, they tend to live in two states, either low activity or high activity states. Or if you're in your kayak, you have two stable states. The preferred one and the less preferred one. Or you can go and you can start thinking about us, our minds, or any animals. The stress axis, in many situations when we're threatened, we make a choice between fight or flight. In our moods, our moods tend to be one or the other. You're depressed, you stay depressed. It takes a while to flip you out of it. Or we get at different levels of manic, depending on our character. Or eating disorders. It's people are trapped between purging and gorging. It's the very many situations in which we find these alternative stable states. Once you start thinking about it, you see them all over the place. So remember, I'm talking here, but those examples I just gave are all out here. The real examples are all very complex situations. But they are exhibiting the type of thing that we'll be talking about in the simple system. Sudden dramatic change can and does happen in these real systems. So we would hope that it will happen in the complex models of those systems. And we hope that we will draw information about those models from the intuition we can find in the simple system. Now let's talk about resilience. So one way to define resilience, this comes mainly from the ecological community, is how much perturbation a system can withstand. So suppose the system is at state C, and we perturb it to here. What will happen? It'll go back up to C. It'll recover its state. It will recover its original function, so it withstood that perturbation. Now let's perturb it down to here. What will happen? Yeah, it goes down. It goes to the new state, so regime shift to state, this new state. So it does not recover its old state or its old function. Let's think in terms of the lake. Suppose the lake was beautiful and clear, but for some reason, for example, the nutrient or phosphorus loading that comes from fertilization of the local agriculture, that runoff into the lake, can bring it down here. And then what's going to happen to the lake? It's going to get turbid. It's going to shift to the turbid state. One of the things you can... Okay, so the question now is, how much do we have to fix to get the lake back to a clear state? How far do we have to perturb it? Up here? No. Just to the other side of B. This is how... Once we understand, this is how much we've got to fix, that's all. So if we can... if it's in the turbid state, and we can bring it there, which is done, for example, by removing some of those bottom feeder fish, so they stop stirring up the sediment. Once you get it there, it can self-recover to the clear state. So it's a useful thing to understand. So in terms of the math, in this situation, resilience, we've just figured out, is the radius of the basin of attraction. The basin of attraction is the set of points that will get attracted back to the attractor. And the radius of the basin of attraction is the smallest edge. That was beautifully precise. You see what I mean? The radius is from C to B. It's off to infinity up above. But the radius is that distance. So it measures the most extreme perturbation the system can withstand while maintaining function. So again, we just talked down here, but if you're thinking up here, attractors have basins of attraction. How would we measure the shape and radius of those basins? And if you have many-dimensional system, then think about the different dimensions and the radius of the basin in those different dimensions as you vary different parameters. Now we'll put all this in a gradually changing environment. And as we do that, I would like to channel my father. So this is my father, Sir Christopher Zeeman. He was knighted for his beautiful work in mathematics and mathematics education. And this is not me, but it could be me. It shows you the environment in which I grew up. Math is just fun. And I highly recommend that you go Google Christopher Zeeman Christmas lectures. And there are 6 lectures he gave in 1978. They were called Mathematics into Pictures. The first 3 are on pure mathematics, and the last 3 are on applied mathematics, and the last 1 is on catastrophe and psychology. And so I'm going to draw a lot from his work on catastrophe theory and what I described to you now. So I want to share with you his view of the world that I was lucky enough to grow up with. So he divided the world into discrete things and continuous things. And he divided behavior into discrete behavior and continuous behavior. And then he divided math into these 4 boxes. So discrete things behaving discretely is this box. So things like dice, and symmetries of polyhedra. They are discrete things that behave discretely, and the mathematics that we develop for that is finite probability and finite groups, and he called that the discrete box. Let's go down here. Discrete things behaving continuously. So the discrete things like planets or populations, but they behave continuously, often because of time, because time is continuous. And so we developed ordinary differential equations to deal with them, and we call it the time box. Now let's go here. Continuous things behaving continuously. So waves, for example. And we develop partial differential equations for that. And that's the continuous box. And now up here, we have a lot of names for what happens up here. This is continuous things that surprise us occasionally by behaving discretely. So continuous things that change suddenly in discrete ways. We have a lot of names: tipping points, critical thresholds, phase transitions, bifurcation theory. My father worked in catastrophe theory. He called that Pandora's box. And it's a really fun place to work. So let's look. I'm going to describe a tipping point in the context of a fold bifurcation. And there are other ways to tip, and there are other ways to think about it, but I'm going to talk about this one. And as usual, I'm drawing a simple one-dimensional picture, and the research challenges are, how do these ideas generalize? So let's go back to our example, our climate example. Let's pretend we can lower greenhouse gases. So we wish it were true. Well, let's pretend we can, that we with our actions and maybe sucking them out of the atmosphere, we can actually lower them. So remember what epsilon did. Epsilon was saying how much escapes, how much energy escapes through the atmosphere. So if we lower the greenhouse gases, more energy will escape through the atmosphere, so epsilon will increase. So what will happen to the pink curve when epsilon increases? Go ahead. Shifts up a little bit, that's right. So we'll shift it up. And so then what happens to all the intersection and the equilibrium and the dynamics? Some move to the left, some move to the right. Right? So these two equilibria got closer together, and this one moved to the left. And if we do this a little bit more, let's suck some more greenhouse gases out of the atmosphere. And those two equilibria coalesced, and it's red and purple at the same time. It's attracting from one side and repelling from the other. Red and blue. It's purple. And if we suck even more greenhouse gases out of the atmosphere, there is no attractor up here anymore. We've lost those attractors. We've only got this attractor. So if we actually achieved that, if we sucked that much greenhouse gas out of the atmosphere, we might be in trouble. So there are limits to all our dreams. But what we see, the point really, of course, is that you see how equilibria can coalesce and disappear. And so even if you used to be at this equilibrium, as you increased epsilon, now you don't have any choice. You've got to move down to this equilibrium. Let's go the other way. Let's increase greenhouse gases. We are very good at this. We wish we were not so good at it. That's going to shift the pink curve down. And so these 2 points will coalesce. And eventually they'll disappear. And the only equilibrium left is an Earth with ice caps or no ice, depending how far up this temperature axis we've shifted. So let's stack all those phase lines up together. So as we were changing the greenhouse gas concentration, low greenhouse gases meant that we only had snowball Earth. High greenhouse gases meant we only had the low ice equilibrium. And they all stack together like that and create this picture for us. So you know how to interpret that. It's a curve of stable equilibria, a blue curve of unstable equilibria, and then stable equilibria again. And if we choose low greenhouse gas, then all our dynamics say that we'll be at the snowball Earth state. And if we have high greenhouse gas, our dynamics say we'll be at the ice caps or no ice state. And our actual situation apparently is, according to climate measurements, somewhere in between, so that we're capable, with our current atmosphere and our current amount of solar insolation, we're capable of either a snowball state or ice caps or ice-free state. So remember that question. How did we get out of this stable state down here? So you were right about changing the atmosphere, changing it through volcanism. So as we study that, let's watch what happens to the resilience of the attractor. So down in the snowball state, what happens, the Earth is covered with ice and snow, and so the volcanoes can still poke through. So volcanoes can still send greenhouse gases into the atmosphere. But our mechanism now for pulling greenhouse gases out of the atmosphere is through weathering of the rocks and through the ocean and through mechanisms that were not available because they were all covered with ice and snow. So greenhouse gases were being put into the atmosphere and were not being drawn out. So we were moving this way, gradually, slowly, along the greenhouse gas axis. And so as we move along, we track this attractor. We're down here, and we move along, and we move up to the new attractor. And look what's happening to our resilience. We're in this snowball state, but our resilience is decreasing. And so as we keep increasing the greenhouse gases, way above what we are at now, the resilience of the snowball state is really shrinking to nothing until finally it's gone, and you jump up to an Earth with no ice. A very hot Earth. And now, once you've done this, you jump up, you get very hot, everything melts, and so now all those mechanisms for drawing greenhouse gases out of the atmosphere, for drawing carbon out of the atmosphere, are accessible again. you have rocks, you have ocean, and so now the greenhouse gases decrease, are drawn out of the atmosphere somewhat, and so we get down to a level like this. But notice that as we reduce the greenhouse gases, we stay now on this upper branch. We stay at this upper attractor. Before, when we had this level of greenhouse gas, we had a snowball Earth. But now, because we've started at this attractor, when we change the level of greenhouse gas, we were at that point, and so we get drawn down to this attractor. Now let's just make clear, we said we've seen evidence of snowball Earth about 600 or 700 million years ago. Here's a proxy for temperature, the temperature record over the last 70 million years. So this is now. Oh, this is now. This is 70 million years ago. And here's a rough temperature range, global average temperature. This, in here, in this last 500,000 years, 400,000 years, these are our recent glaciation events. So here we are now. So 400,000 years ago, there was, it was like now, and then we gradually got colder and colder and colder. There's glaciation, and then a melt, and then we got colder and colder, and then a melt. So this is glacial, interglacial events on a roughly 100,000 year cycle, all squeezed in there. And there's all this other stuff that's happened over Earth's history, just the last 70 million, just recently. So I just want to make clear that last 70 million years is moving around here. Our model does not capture it at all. It doesn't capture any of those intricacies. But do notice that there are lots of interesting abrupt events here. Look at that sudden change. And that sudden change. And this thing, this sudden thing. So it screams for more models looking at what are the mechanisms behind those things that look like they were tips. Oh. So anyway, going back to our model, if we continue decreasing the greenhouse gases, then we'll jump back down to snowball if we decrease too far. So the point to make here is we jump at different points. Right? This is hysteresis. The fact that on the way up, we jump up at this high level of greenhouse gas, but to recover from that, we have to descend much further. So the irreversibility that's associated with tipping points, in this context of a fold bifurcation, you can think of as hysteresis. Let's look at that in the shallow lake example. It was shallow lakes, it's the nutrient loading, that if a shallow lake is turbid and you're able, sorry, let's start up here. If the shallow lake is clear, notice the axis is backwards for this picture. If it's clear and you increase the nutrient loading, so you make it higher and higher, then it jumps to turbid. And you have to pull the nutrient loading back a long way before it will jump back up to clear. There is experimental data confirming that. In the neuron, remember that neuron that was firing back and forth? The slow variable there is calcium. You can take measurements. These measurements were taken at the same time from the same cell. When the cell is quiescent, the calcium gradually decreases. When the cell is firing, the calcium increases. So there's this intrinsic mechanism in the cell. So it starts quiescent, and calcium increases. And as calcium increases, we lose resilience of the quiescent attractor, and so we're forced to jump to firing. But then when the cell is firing, calcium decreases. So these internal dynamics of the cell bring you back down, and so you see the cycle back and forth. When you jump down, the calcium starts increasing again. Toy disc. This is my toy disc. It has a state that's concave up and a state that's concave down. And it tips. I'll find it. Can't lose my toy. So it's the physics inside this little thing that makes it tip. This is one of my favorite toys. Same thing, only I can take control of this one. You can use the fact that it's going to tip to your advantage, right? So there are different ways of thinking about tipping points and the whole tipping phenomenon. So finally, on that note, let's think about decision support. So we've said that the resilience is the ability of the system to withstand perturbation. And as we approach the tipping point, the bifurcation here, the resilience is shrinking. Can we exploit that structure? We're mathematicians. When we see something, we want to really extract all the structure we can, all the patterns associated with this, and see how we can use it. So I think of this in two different cases. Case one is when we don't have control over the gradually changing environment. So that's like the climate. We don't have a lot of control over it. We could have more. This slide I borrowed from Martin Scheffer. So he asked the question, can those critical transitions or tips be predicted even if we do not understand the system? So he's saying, we spotted a pattern here. Let's just test it here. Even though we don't understand this system, let's just test that pattern. Does it give us any insight? So what are the patterns that he tests? He points out that a lot of these systems live in a stochastic world. And maybe we can probe that, we can use that stochasticity to probe the system. So let's think about how to do that. How does the system respond to stochastic perturbation? As the resilience shrinks, at what rate is the system changing at that point? So is the system changing when it's at this point? I mean literally that point right there. I'm being obnoxious. It's an equilibrium of the system. So it's not changing there, right? Yeah. So you're doing the right thing, only I'm going more slowly. It's not changing there. It's also not changing here. So is it moving very fast in between? That's the question. Here the system was not changing there and not changing there, but it had plenty of time to speed up in between. In between these 2 points, there is not much time to speed up. It's moving slowly. As you approach a tipping point, the system moves more slowly. And if your system is noisy, so it's perturbed around this, you're always getting these little perturbations, you can measure how fast it responds to those perturbations. Or you can ask, is it responding fast to those perturbations? So how does the system respond to stochastic perturbation? You have this thing called critical slowing as it approaches the bifurcation, as it approaches the tip. And the rate of attraction to the attractor slows down. And so what will that do? What patterns will that create? Your perturbations will die down more slowly. Increased autocorrelation. What does that mean? If you're just taking observations, if you take an observation, then the next observation is more likely to be similar to the previous one because it hasn't changed much, because it's changing slowly. Over here, the observations will look very different from each other because it's moving fast. Also, increased variance in behavior, because over here, the system quickly recovers, and so what you'll mainly see is the attractor. But over here, the system doesn't recover quickly, so you will see all those perturbations. You'll see more of it, so you'd expect to see more variance. So there's a lot you can draw from the fact that that you have two attracting states coalescing. That's what's really behind this. And that they do not have to be equilibria, right? Be thinking complex system. Two attracting states coalescing will have that phenomenon. So Scheffer has tested this in some of these points, these interesting sudden changes on the recent paleoclimate record. And so this again is a slide I borrowed from Scheffer. And so he's taken bits of data. These four are zooming in on the climate data. Here are 4 different tipping times, right? Sudden changes, abrupt changes. And the pictures underneath are the autocorrelation. So how similar is the observation from the previous observation? 0 means not similar at all, and 1 means very similar. And so this guy, what happens as you approach each of these tips is that the autocorrelation gets higher. So he's seeing that pattern that we predicted would happen from the simple one-dimensional system is being observed in this big complex climate system. So it's very interesting. He spotted a pattern there, he tested it here, and it's interesting how often it works, which is inspiring new research questions, or it creates inspiring new research questions. It opens a wealth of questions to study. Case 2 is the case where we think about policy decision context, when we do have control over the gradually changing environment. So it might be lakes or farmland or water or whatever it is, the urban planning, maybe our atmosphere. So then we have a way of, we have a history of managing for efficiency. There's a book I like very much called Resilience Thinking by Walker and Scott, just Resilience Thinking. If you Google that, you'll find it. Walker and Salt, sorry. And they make the point that managing for efficiency is not the same thing as managing for resilience. And maybe we could be changing the way we think about optimization so that we're bringing in a lot more size of basin into our optimization algorithms. Because what we would like, if we are planning for an uncertain future, and for a future with perturbation and increasing size perturbation, we would like to keep the basin of attraction large enough, whatever that means. And then, what if the policymaker has more than one dimension of control? So all the pictures we've been drawing so far today are one-dimensional pictures, meaning one-dimensional of environmental change. So I'm going to channel my father just for the last couple of minutes again. This is him and his catastrophe machine, for which he's famous. This is the generic situation, the generic equilibrium surface, if you have 2 dimensions of control in a system which has some kind of minimizing principle in the dynamics. So the minimizing principle means that you have equilibria. That you're not attracted to periodic orbits or strange attractors, you're attracted to equilibria. And if you are, then there are not many complex ways that the dynamics can evolve. You could just have a folded surface that's just folded like we saw before. But the other generic picture you can get is this one. So here at the front is the picture we've been working with all the time. And that my father would call the normal factor. And so when we're worried about tipping, we're worried about how far we're moving back and forth along this normal factor. But there's another factor to look for. It's the splitting factor, right? So there are other ways of avoiding the sudden jumps. If you move back in your control space, if you have this option, you can move back in this control space and you can just move away from this low resilience area. If you can visualize that as you move backwards, your resilience increases. There are many paths to get from here to here. Some of them involve this rather dramatic route. Some of them involve a much more gentle route. And so some things that are that create splitting factors, some things that pull you forward, are the strength of the feedback. We were talking about the feedback mechanisms in the lake and the climate. They pull you forward to make a more extreme hysteresis situation. Network connectivity can do that. The more connected your network is, it can pull you forward. In the lake situation, the depth of the lake pulled you back. A shallow lake suffered this, but a deep lake is better adapted to the changes to having algae at the top because it's already got plants that know how to deal with darkness at the bottom because deep. In the neuron, it's the ion channel distribution that's controlling whether or not it's multi-stable. So I think that, again, that's another pattern that we could exploit. There's a pattern there that we've looked at, that my father and the work on catastrophe theory way back when, 30 years ago, in our lifetimes, looked at that pattern and enjoyed that pattern. I think we could enjoy testing it and looking for what it tells us about the more complex situation, because I think it could offer us insight into policy options that we may not be thinking about yet. And so with that, the reminder, if you would like to hear more, if you would like to learn more about that, go Google his Christmas lectures. And thank you.